Hello and welcome to this lecture on deflection calculations in beam bending. In this lecture, I'm going to first explain how we would find out the elastic energy stored in members under tension, bending, torsion, and shear. Once we figure out how to do the calculations for the energy stored, there is a method that we can use to utilize the calculations of energy storage in finding deflections and rotations of beam. So in fact, there's two elements of this presentation or this section. One element is number one, how to find the elastic energy stored in a section of a beam or a tension member or a torsion bar. And then number two, once you find that out, how do you utilize the expressions or the formulas that you'll get in determining deflections or rotations. So let's start the idea now by looking at energy stored in a very simple system, which is usually a tensile bar or a member under tension. So in this case, we have the energy stored. U is the product of the force average, so this is important, times the distance y that moved. Let's say that we have a force and the force is moving a distance y on this axis, and the force starts from 0 and then it becomes capital F at the end of the displacement, at the end of the y displacement. So it starts from 0 and ends at F. Therefore, the average force is F over 2. So during the displacement, the average force is F over 2, and the displacement is y. And therefore, we would have the elastic energy stored is F over 2 times y. However, we know that there is a relationship between the force and the displacement, that F divided by K is equal to y. We have derived this equation before, utilized it before, and therefore we can write two forms of the energy stored, one that is apparently linear in y, or linear in F, but if we utilize the relationship between y and F given here, we can get the energy stored to be F squared over 2K. So you will see that this is very general, and if we look at the elastic energy stored per unit volume, for example, it is equal to sigma times epsilon, and now we just have to write the equation for sigma and epsilon, and if we have like an average value for for sigma, which represents the force, then you have 1/2 sigma times epsilon. So if you have epsilon is equal to sigma over E, then you have sigma squared over 2E, or equivalently we can write it as E times epsilon squared over 2. So this is per unit volume. Per unit volume. And we could actually find now for various applications what is sigma, what is epsilon, and then integrate over the volume. Going through that, we see that now we have some common strain energy formulas that you can see here. If we look at the previous equation, that we have U is equal to F squared over 2K, then we can write this equation using the fact that if it is a member under tension, that the member under tension will have a force F, and the area here is A, and the length is L. Then we have shown that previously that the effective stiffness of that spring is AE over L. Once we substitute that in the equation for the energy stored, then we get the total energy stored as equal to F squared L over 2AE. And if I want to have it for a short segment, for example, so if I want to write U for a short segment, if let's say du will be equal to F squared dx over 2AE. So instead of L, I can write it as dx because it's a small amount of energy. If I integrate the left-hand side and the right-hand side, I get the total U, which is this equation here. This is the total U, the energy stored in the tensile member. So to summarize, here the formula that we use is that for a tensile member, we have the energy stored is equal to the integral of F squared 2AE divided by 2AE times dx, and then we integrate this over the length of the member. So this is the procedure that we have shown from the simple tensile member, that the energy stored will be the integral of the 4 squared over 2AE dx. We can proceed with the same idea again for members that are under bending, where there's no force but there is a moment, or members under torsion where there is actually a torque applied, or members under direct shear. So for all of these applications, the procedure is very similar, and we state here the formulas that are derived. So if we look here at the case for torsional loading, the torsional the stiffness K is equal to GJ over L. We have also shown this. Notice that it is very similar to the tensile stiffness, and the fact that you have the torsional rigidity, which is the product of GJ, and on the top, and then this is divided by the length of the torque member. So if again we're using this, we can find that the total energy stored for a member under torsion and the length of the member is L. Then we get this equation T squared L over 2GJ. Or if L, we take L to be very small, would be dx, and then we integrate over x. We then get a more general form of the torsion energy stored in torsion, that is the integral of T squared over 2GJ. So there's a similarity here. For direct shear, the procedure is similar, and therefore we'll borrow the same idea from tension. From tension, we find this F squared over 2AE dx. For shear, it will be F squared over 2AG, because G now is for shear rather than E is for tension. And because it's the same procedure for finding the energy. So in this case, we have exactly the same formula, but replacing G with E. For bending loading, the stress, the bending stress is M times Y over I, and we could use that and find the bending strain. And then we would use the previous formula that I described, which is a general formula for the energy per unit volume. This energy per unit volume here, we're substituting for sigma squared over 2E, for example, then and integrating over the volume. And the sigma is my over I. And when you integrate over the volume, you get square of m, and then the y, when you square it and integrate over the volume, you get another second moment of area, and therefore the end result is that for bending loading, the internal energy stored is m squared L over 2EI. again for general case with a dx integrated over the length. So usually we the area, cross-sectional area, is constant along the path of integration, and therefore the integration will be just over the length of the beam dx. So it'll be integration of m squared over 2ei times dx and integrated over x. Finally, if we have transverse shear, which is different from direct shear, the difference between transverse shear and direct shear is that direct shear is uniform over the cross section. It doesn't vary over the cross section. Like you're shearing an object and you have a shear strain as constant and you have a shear stress as constant. So in this case, we use the previous formula, which is the integral of f squared over 2ag dx. However, if we have transverse shear, like in beam bending, for example, then there's a distribution of shear stress over the cross section. That distribution gives you another factor when you do the integration that would amplify the value that we obtain if we have uniform shear across the cross section. So in this case, we just have an additional factor C. V now is the force, but is now specifically the transverse shear force. And therefore we use the same formula as for direct shear, but with a constant C. And the constant C is obtained from integrations and is done for us. For example, for circular cross section is 1.11, and for rectangular cross section is 1.2, and for a thin-walled tube is 2. So now we finished all of the equations, describing the equations without getting too much into the derivations, although the derivations are quite simple. And we have now a summary. So in this summary, you will see that I have formula for, let me just make it the general one. So the formula for tension is f squared over 2ae. For torsion is t squared over 2gj. For bending is m squared over 2ei. For direct shear is f squared over 2ag dx. And for transverse shear, you just add a constant c, v squared over 2ag. And thus, we have all of the available formulas for us to compute the elastic energy stored in any member under tension, torsion, bending, or shear. And we can think also of that member once we calculate the elastic energy stored as a spring. So it's kind of storing the energy in there. So let's take an application, quick application before we end the lecture. So in here, we have a cantilever beam that is loaded with a force F at the end, and we want to find the strain energy stored in the beam. So this is the idea, is that we want to find the strain energy stored in the beam as a requirement. So in this case, I have the moment is we're going to have a moment that is curving the beam downward in this direction. So it'll be a negative moment, will be minus f times x, because if we take a distance x from the tip, and then we have to integrate now m squared over 2ei dx to find the total energy, which means the integration of fx squared over 2ei dx to get the total energy from 0 to L. So let's see how this will work, and then we also need to include the direction to assess or to determine the amount of energy stored due to direct shear. So for direct shear, the shear force V is equal to F in this analysis. Therefore, the energy stored in direct shear by applying the formula, we have since the cross section is round, then we have 1.11 F squared L over 2 AG. For bending, we do the integration, so F squared integration, it gets you L cubed. So the total energy, which is energy stored in bending, energy stored in shear, the energy stored in bending is proportional to L cubed, and the energy stored in shear is proportional to L. So you can see now that as the beam becomes longer, you store more energy in bending than in shear because it depends on L cubed. And therefore, we would expect that if the beam is long and slender, then most of the energy will be stored in bending. But if the beam is short and stubby and has a large cross section, then a significant amount of energy can be stored in shear. So for this example, let's just kind of determine the percentage to make sure that the amount that is stored in shear is not very significant. So if we look here, we can actually input the values in here. All right, so I think I'm going to stop at this point, convenient point, and I'll pick it up next time where we will indeed discuss the Castigliano's theorem, which will allow us to determine the displacement or rotation from the dependence of the internal energy stored on the force. So